So welcome back, everyone. So for the second talk of the day, maybe one practical announcement. So all the talks are being recorded, and they should also appear on the website of the KNAW, hopefully somewhere next week. So if you want to listen to talks again, look at the slides again, you'll have this opportunity. So the second talk of today is going to be given by Andrej Bauer, whom I will introduce. He's a professor of computational mathematics in Ljubljana in Slovenia, working on constructive logic and mathematics, type theory, theory of programming languages, and proof assistance. So he obtains his PhD from Carnegie Mellon in 2000, and his supervisor was Dana Scott, already mentioned earlier today. He won a prize with his dissertation from CMU. So it's, actually, this is one of these PhD theses that was extremely helpful to me when I was doing my own PhD. So there are a few, like also Matthias Manni's PhD thesis was extremely helpful to me. So it discusses things related to category theory, topology, computability theory, domain theory, computable analysis. And these are also the areas in which he has worked during his career. So a wide range of interests, and also someone also whose talks I always look forward to. Actually, he also won. I mean, maybe also nice to mention that he won a prize for the best expository paper in the notices of the AMS on the 5 stages of accepting constructive mathematics. This is a paper that I can recommend to everyone in the audience. Another interesting work that he's done has been on the reals being countable, also more recent work. But today he will also talk about related topics, so the effective topos as a world for computability theory. Which is joint work with Andrew Swan, who is also here in the audience somewhere hiding over there. Yes. So yeah, I'm looking forward to this. So please.
Thank you. Thank you so very much for having me here. It's a great pleasure, and especially it's a great pleasure that I can participate and speak at this event in honor of Jaap van Oosten and celebrating his work. And I should add that we should also celebrate his sense of humor, as anybody who has been on the receiving end of it will certainly agree with this. Today I would like to speak about synthetic computability and the effective topos, but so as I was thinking of this talk and what to say, Albert Visser said, "Oh, but please make sure that you explain all the basic concepts," to which I replied, "Well, how do you know there will be any in my talk?" And so, but then I came to my senses, because he said, "Well, but there will be 100 people. I counted you. It's not quite 100, but it's good enough. It's 84. So I decided, okay, so I do have to give a reasonable talk, and not like an unreasonable one that 3.5 people in the audience will understand. So I'll try to do that. But in order to do that, I'll spend some time explaining what the idea of synthetic mathematics is. And then we're going to look more closely at how synthetic computability is done. And this is where Jaap's work becomes most important. And to add something new, I'm going to finish with the recent work that I've been doing with Andrew Swan on Turing degrees in synthetic computability, because that's not something that has been done yet. And any kind of synthetic mathematics, in order to really deserve its name, has to be able to cover at least the basic concepts of whatever branch it's supposed to deal with, and Turing degrees are certainly a central concept in computability theory. Okay, so what is synthetic mathematics? You might have heard, or I'm pretty sure you did, about the two approaches to geometry, namely Euclid's synthetic geometry versus Descartes' analytic geometry. So what's the difference between these two? So by the way, before I go on, so these, of course, is some form of Euclid's elements, and the other one is Descartes. I don't speak French, but can somebody tell me, does this title say that it's about meteors and geometry? Mm-hmm. Yeah. So that's, like, you couldn't publish that today. Okay, anyhow. So the Euclid's approach is sometimes called synthetic, and it proceeds in a certain way that's different from how Descartes does his geometry, which is analytic. And so what are the two characteristics? So in one of them, you take some basic objects as primitive. So for instance, points and lines, right? Careful in the Euclidean style synthetic geometry, lines are not sets of points. There are no sets. Lines are primitive objects there. So then we axiomatize their properties and relations, and to be quite fair both to Euclid and to the more recent developments in logic, one should say we also postulate constructions, because they are like operations, and constructions are equally important. And then we work strictly within the given axiomatic system. So we are very careful not to use anything that's outside from what we postulated, and we prove theorems there. The analytic approach is a little bit different. There we actually construct our objects of interest from some other objects. For instance, we might say that a point is a pair of real numbers, thinking of the coordinates. And so then a point would not be a primitive object. A real number would be, in this case, a primitive object. And then we don't have to postulate any axioms. We just use our construction to analyze the situation, therefore analytic. And we deduce the desired properties and relations. This usually then happens in some foundational system. So today, this would likely be some sort of set theory, or if you're young, it would be type theory. It doesn't really matter, but it's going to be a foundational system, a wider system within which we want to do this. So I think Euclidean geometry can serve very well to illustrate this point. Now, what is synthetic mathematics? We want to apply the same sort of idea, but not to a single structure such as the Euclidean plane, but to an entire branch of mathematics. So also an entire branch of mathematics can be tackled this way. Why is this maybe a little bit strange? Because you almost exclusively see only the analytic approaches to branches of mathematics. They would, if somebody wants to explain to you what is topology, they would probably start by saying, well, a topological space is, and they're going to explain how a topological space is built from some more basic objects, whether they are objects in some topos or whether they're sets or types. Nevertheless, it's going to be analytic in nature. But we can also think, well, is there a synthetic way? And in fact, yes, there is a synthetic way, and there have been many of these. So, for instance, I would say maybe, I'm not very good on history here, but probably non-standard analysis would be a very early one with the ultra power constructions, which would be the analytic way, but then non-standard analysis also deals with the axiomatic system for non-standard analysis. And then of the kind that I'm going to talk about, a different one is synthetic differential geometry. So this one was developed by various people. I'm almost afraid to try to list them. So Eduardo Dubuc and Levere and Anders Koch. And there is a very nice book by Ike Moerdijk and Reyes, who Ike is here somewhere. Yes, I can recommend the book. So it was very inspiring to me to see how, what this idea of doing things synthetically is. Then in the 80s, Dana Scott, I think, was probably motivated the development of synthetic domain theory, where the idea was to find an axiomatic way to do domain theory, which would then hopefully also be simpler than some of the domain theory that was coming up at the time when there were many kinds of domains and some of the constructions were getting over the heads of a typical computer scientist. And then out of domain theory, some other variants grew, like, for instance, there's synthetic topology that was promoted and studied by Martin Escardo and Paul Taylor in various forms, and also a little bit by myself and my student, Davor Leshnik. I'm going to say more about synthetic computability, of course, but let me also just note that homotopy type theory, the new kid on the block, is a kind of synthetic mathematics, and it has in fact been called synthetic homotopy theory. If you know how circles and spheres are handled in homotopy type theory, well, that is the kind of synthetic way of doing things, if you're familiar with that. And there's even a newer kid on the block. There's some recent further development in the direction of synthetic algebraic geometry by Tyriko Khan. This was started with Ingo Blechschmidt's PhD, I think, is maybe so he seriously attacked this, and there has been some exciting progress recently. So people think about this. Okay, so we're going to focus on synthetic computability. But as logicians, let's explain a little more precisely what I'm talking about, because it's not that complicated. One way to see these two sides is to simply say, well, on the synthetic side, you have some sort of a logical theory. And then on the analytic side, you have a model. So if you think about, for instance, let's think about non-Euclidean geometry. Well, there will be some axioms of non-Euclidean geometry. And then there will be models, which will be these curvy things, right? So that will be the models. And there's an interpretation that connects them. Now, if you want to do this with a whole branch of mathematics, so not a single structure, so you don't want the model to be just a surface with some stuff in it, then this is going to go a little bit more grand scale. And one way to do it is the way that Andy in his talk was indicating, is that you use toposes because they're rich enough to support the things that we want to do, that namely that we want to have all this, we want to have a richness of structures. And the appropriate kind of theory in general would be intuitionistic higher order logic, which Andy already talked about. Now, you can do a lot in this generality, but of course, in order to really grab a particular kind of synthetic mathematics by its horns, you want specific kinds of toposes. So you would want to say, no, I don't want general toposes. I'm going to narrow it down maybe to just a single topos or a certain family of toposes that have some very special properties. Now, these very special properties should be chosen in such a way that they make reasoning in our desired branch of mathematics as nice as possible. On the synthetic side, or that is to say, on the side of the formalism, that means that rather than having just intuitionistic higher order logic, we're going to have some specific axioms. So for instance, this might be like countable choice, or there might be some very specific axioms about rings or whatnot, but you try to find some axioms that will capture the spirit of what you're trying to do. And in order to know that you're not doing something insane, of course, then you want to have corresponding specific toposes and models, because that will both tell you that it's consistent, but also it'll inform your theory and it'll give you ideas on what to do. Okay? So in synthetic, by the way, so now by choosing different toposes, you can do various things, and people have done various things. And it's very nice, because you don't get just one paradise for one person. Everybody gets a paradise, right? So you, for instance, The first one, in synthetic differential geometry, you're going to have statements which are classically impossible. They're not allowed. So for instance, all maps are smooth. This is like a physicist paradise because they can just differentiate anything they see, right? Which they do anyway. So, you know, maybe that's not going to be the physicist's view. The physicist might say, oh, you finally came to your senses. And you know, and this goes on. Like, for instance, in synthetic topology, for fairly trivial reasons, you're going to have the statement all maps are continuous, and everybody will be very happy because, you know, all maps are continuous in topology. And similarly, in synthetic computability, and more particularly in the effective topos, it's going to validate the statement all maps are computable, whichever way this is precisely stated. You should, you know, these are somewhat informal statements here. I did not explain the details, of course. So this is looking very good, you know, but you know what happens when it's too good to be true, right? So you start digging a little further, and so you say, oh, but the effective topos, it's even better, right? It also shows that all maps are continuous. That's known as the KLS theorem, Kreisel-Lacombe-Schoenflitz. Actually, it should be KLST theorem, Kreisel-Lacombe-Schoenflitz-Zeitin theorem. And so that for a different reason than in a typical sheaf topos, in this topos also all maps are continuous. And this is all very nice. But then you read Russian literature on recursive analysis, and you realize that in this topos, there is an unbounded map from the closed interval to the reals. And then if you put the second and the third statements together, this is becoming a little bit worrisome because now we have a continuous unbounded map on the closed interval. So what's going on with our paradise? Well, this is only the beginning, actually. So, for instance, also, there is a set which is neither finite nor infinite, literally, okay? And a certain kind of ordinals, you have to be a little careful how you define ordinals because we're in an intuitionistic setting, but the trichotomous ordinals form a set. So this is strange. It's a strange world. However, these statements all relate to known facts about computability theory. So for instance, well, the unbounded stuff, that's just Russian recursive analysis. It's been long for a long time. But a set which is neither finite nor infinite, if you calculate what that says in the effective topos, computability theorists will recognize that as an immune set. And computability theorists will say, yes, we actually do think about an immune set as something that is computably neither finite nor infinite. This is how the effective topos works as the synthetic world of computability. It's the one in which various slightly informal intuitions about how things are in computability theory become rigorous mathematical statements in a very naive way. Like literally, there is a set which is neither finite nor infinite. You don't have to say anything about computability. It's precisely what it says. The trichotomous ordinals, if you're a computability theory, I just have to say one thing. Omega 1 Church-Klini. Okay? And then you say, okay, yes. So the trichotomous ordinals, because everything needs to be computable, and so the trichotomy means that you can decide their order, will tell you that computably can only go up so far, and you're going to get a set. So that's why this is going. It's not surprising if you're a computability theorist. It might be a little more surprising if you're not a computability theorist. Okay. So I would like to mention two further synthetic worlds that I've worked on, especially because they are also relate to YAP, okay? So the first one is this. If you just take the variant of the effective topos where you replace Turing machines with Joel Hamkin's infinite time Turing machines, you're going to get a realizability topos. And in that realizability topos, the space of sequences n to the power of n, so that's the space of all integer sequences, it embeds into the natural numbers. And I can tell you that I was highly motivated to find one such topos when Jaap visited Ljubljana a while ago, and he spent a semester there, because he strongly disbelieved that this is possible. So thank you, Jaap, for giving me the motivation. I was very motivated to prove you wrong. And then there is some more recent work with James Hansen and me, in which we found a topos in which the object of the Dedekind reals is countable. And I find that extremely surprising. How does this relate to Jaap's work? Well, the word there is parametric realizability. So this is a new kind of a variant of realizability where your partial combinatory algebra is additionally parametrized by a set of parameters. And then the notion of realizability, your notion of realizability has to be uniform in those parameters, and then things work out in a certain way. And then you can find a particular one of that kind in which the real numbers are countable. So this is a specific construction. But Andrew Swan observed and told me, and probably nobody else, that every parametric PCA is actually of the kind that you can find in Jaap's book, where he explains how to adjoin an oracle to a PCA. And so up to equivalence, all these examples arise from Jaap's construction. So this is something that we learned after we already found all these results, and then it was observed that construction of Jaap's is quite important here. Okay, so where do we go from here? Let's speak about synthetic computability a little more precisely. So in this case, we're going to focus on the effective topos, and we would like to interpret the intuitionistic higher order logic. There ought to be some specific axioms of synthetic computability that are valid in the effective topos. And then when we work synthetically, we would just use those axioms and nothing else. We want to completely forget that there is an underlying model, and we never want to look at it again. So I suppose I should try to define the three pieces in this slide, so the first one would be the effective topos, but I know better than to try to define the effective topos in a talk. I already tried a couple of times, and I do not recommend it to anybody. Nevertheless, there is this great book where you can read about it. It's Jaap's book on realizability, which I always keep within reach because I looked at it very often. And even when I have to look up what a tripos is, I don't look at the paper of the person sitting next to you. I look at your book. Yes, yes. So thanks for the book. It's not very important to know precisely what the effective topos is for this talk, even though everybody should, because I will focus on the synthetic side. Now, if I try to explain what non-Euclidean geometry was, certainly one way would be to show you a sphere and hyperboloid and stuff like that. But there's another way. I would just show you the axioms, and then I would hope that your mind eventually would develop some intuition about what these axioms are about, and I might draw some informal pictures of things to help you. And that's how you can actually approach any synthetic subject. I can tell you what you would get if you interpreted certain statements in the effective topos, but we're not actually going to do so because it takes time and it's technically complicated. But I'll help you with that. Okay. So what are the axioms of synthetic computability? As already said several times, we're going to work in intuitionistic higher order logic, which has a bunch of constructions. Among other things, it has the object of truth values and the natural numbers. And essentially, you get enough math to do everyday math. So this is enough to construct the real numbers, to do like undergraduate analysis, complex analysis, combinatorics, like all the normal math. So what abnormal math can you not do? Well, if you want to do strange forms, like if you want to do huge things or like something that requires more logical strength than what you get out of this, then of course you cannot do it, right? So vaguely speaking, this is like bounded Zermelo set theory, vaguely. Okay, so that's that. What are the specific axioms? So one specific axiom that we need is dependent choice. But here I should say two things. Actually, in most applications, we only need countable choice, so choice for countable families of sets. In a few places, we need slightly stronger choice, which is choice of not stable subsets of natural numbers. This is a technicality that I don't want to get into. I can just tell you that I only used this once, which was to prove the synthetic version of the KLS theorem. All maps are continuous. There I needed it. I didn't see a way around it. A more interesting one, well, there's one that's still not interesting, which is Markov principle. So Markov principle is valid in the effective topos, and it comes in handy because it really allows us to simplify things in a couple of places. And this is my preferred formulation of Markov principle is, you have to make your axioms sound really obvious. So here's one. If a binary sequence is not all zeros, then it has to contain a 1. That's Markov's principle. It looks deceptively true, right? It looks like, how could this fail? If you're thinking to yourself, how could this fail? You're not yet at stage 5. The central axiom of synthetic computability is the enumerability axiom. And it says that there are countably many countable subsets of natural numbers. Now, we should take 30 seconds to think about this. Okay, so here's how you should probably digest this. So your first observation should be, but isn't every subset of the natural numbers countable? And aren't there uncountably subsets of natural numbers? Okay, so of those two, the first one is false intuitionistically, and the second one is true intuitionistically. So yes, intuitionistically, there are uncountably many subsets of natural numbers. But not every, you cannot show intuitionistically that they are all countable. Countable because countable means you can actually enumerate them. And I can tell you why this would be the case in the effective topos. You cannot enumerate computably the complement of the halting set. That's a co-CE set. So you cannot. Right? So that would be an example in the effective topos of a subset that isn't enumerable, countably enumerable. Because when I say countable inside the topos, that automatically means that in the model, it'll have to be computably countable. And not all sets are computably countable. Why are there countably many of them? Because there exists an acceptable enumeration of CE sets. That's all there is to it. So if you're a computability theorist, this is totally obvious. There is an acceptable enumeration of CE sets, of computably enumerable sets. This axiom is wonderful. It has wonderful consequences. Among others, also that excluded middle is false. So it's an anti-classical axiom, and we have no choice but to throw away excluded middle in general. I mean, of course, instances of it still hold, but in general, we cannot accept it if we want to have this axiom. And this is a general feature of synthetic mathematics, at least of the kinds that people have often studied. People like in my bubble, social bubble, and that the toposes that arise in synthetic mathematics tend to be intuitionistic. So it's more of an empirical observation that excluded middle is gone. It's not something that we really have a freedom to choose. The synthetic method goes vaguely like this, okay? You take some classical theorem in computability theory, you open the book, you open Rogers or Odifredi or somebody, and you find a theorem, and then you think about it and say, what does this say about the effective topos? And you find some statement about the effective topos, which is probably a mix of category theory, and it talks about realizers, and you see that somehow it corresponds to the theorem. Now you have to reverse engineer this thing and find an internal statement whose interpretation will hit that fact. And you're going to find something that's not very nice. But by working further, you try to abstract and generalize the statement. It's typically going to be too specific, because you found some specific fact about something very specific. But then you can generalize it, and it's easier to generalize it in the internal language than it would be by working directly in the topos. Finally, you give a proof that is based only on the synthetic axioms. That's the idea. There is a bonus that you can get. You get bonus points if you can actually prove your statement without the axioms, and you just do it in pure intuitionistic higher-order logic. This has happened a number of times, and it's become somewhat of a method of mine. I really try when I synthesize, like when I try the synthetic form, I really try to find a theorem which is just true. However, it typically then becomes difficult to show that it has any non-trivial instances. And that's where the synthetic world comes in. The synthetic world is full of very strange objects that then satisfy some strange properties and give you examples of the theorem, which is just true, but the theorem, for all you know, is trivial. But you cannot show that it's not trivial, and if you work hard, you can find instances. I will give you one such example, and this is an improved version of Rice's theorem in comparison to what was known when Jaap wrote his book, and it has a section on synthetic computability, which, by the way, boosted my already big ego way out of proportion when I saw that it's in the book. So thank you for that as well. Okay, so let's recall Rice's theorem. So first of all, I'm going to write phi sub n, as every computability theorist does, for the nth partial computable map, where the encoding has to be reasonable, and this is a standard notion. And then what we usually call an index set is a set of natural numbers such that if a number is in it, and that number is an index of some partial computable map, then also all the other indices for that computable map are in it. So it's a set that is closed, it's extensional with respect to this enumeration. And Rice's theorem states that the only computably decidable index sets are the empty set and the natural numbers. And we teach this to computer scientists, and we try to explain that this is important for things like implementing optimizers and like asking questions, like expecting the machine to perform certain kinds of program analysis, like you say, well, but it is impossible, but then you do it anyway. By violating one of these conditions, of course. So anyway, it's an important theorem. What is the synthetic form of this? I'm going to take you through several steps and just show you the end result. But you should be able to see that the end result has something to do with Rice's theorem. OK, so say that a set A, oh, by the way, I say set. I really mean object in the effective topos, but just by old habit, I like to say it's set. I could just also keep saying space or something. It's not really important. So an object or a set A has the fixed point. We say that it has the fixed point property if every endomap on the set has a fixed point. And the synthetic Rice's theorem says that any set, if a set A has the fixed point property, then every map from A to the set, to the discrete set on two values, so 2 here is the set of values where each value is either 0 or 1, that every such map must be constant. I'm not going to drag you through the proof, but the complete proof of synthetic Rice's theorem fits on this slide. It's easy. Okay? Once I show you the theorem, I send you away. It's not that difficult to prove it when you think about what needs to be done. It's some blah, blah, blah with fixed points. Okay? Here's the bonus. Its proof is pure. This is a pure proof. Okay? So it just holds. But if I ask you, can you come up with any examples? Well, classically, in classical set theory, that's going to be difficult because the only set that has a fixed point property in classical set theory is the singleton. Right? So the theorem is not terribly interesting because it's a theorem about the singleton set, classically. However, in the synthetic world, the enumerability axiom implies that there are lots of interesting sets like this because, for instance, all omega algebraic pointed omega CPOs, whatever they are, but there are certain kinds of domains, have the fixed point property. So that's nice. And now you should also be able to see that this relates to the classical Rice's theorem because the object of partial maps from natural numbers to natural numbers, where you have to use the correct notion of partiality, is going to be one of these omega CPOs. Okay? So that's how you want to do this. Now, for today, I would like to speak about Turing degrees, because that's not something that has been done yet. There have been people working on it, but I think they're not done either. First, let's discuss oracles. So what is an oracle? It's going to be better to ask what is a partial oracle. So I'm going to define a partial oracle to be a pair, A0, A1, of two disjoint subsets of natural numbers. So the way you think about this is A0 is the set where your oracle says no, and A1 is the set where your oracle answers yes. And of course, the numbers on which you get the answer no and the numbers on which you get the answer yes, they should be disjoint. And we do not require that they cover all of n, so that's why we say that this is a partial oracle. So if you ask the oracle a question about some number that's in neither of these two sets, it remains silent. You do not get an answer. It's an undefined. If you collect all of these into an object of partial oracles, so literally just what it says there, pairs of subsets of natural numbers that are disjoint, that's a very nice domain. It's directed complete. Directed subsets have suprema. You just buy component-wise unions. And it's also omega algebraic, which means that if you calculate, the compact elements there are countably many compact elements, and they form a nice base. This is actually simpler than it sounds, because all that this says is that if you have a set, every set is a union, is a directed union of its finite subsets. That's what this comes down to. And this is intuitionistically completely unproblematic. Every set is a union of its finite subsets. So we have a nice base. This is important because once we have a countable base, we can start doing things with countable choice and so on. So that's going to be nice. It gives us a grip on this. Okay, what about total oracles? So the oracles that are not partial. How would you say that an oracle always gives an answer? And well, that just asks, what are the maximal elements of this domain, O? And you can prove that an element is maximal, so A0, A1 is maximal, precisely when the sets of answers, of positive and negative answers, are complements of each other. Yes? So for the effective topos theorists in the audience, this is saying that nabla 2 to the n is the set of maximal elements of O. So the maximal elements of O are nabla 2 to the n. Here's the wrong thing to say. If you say that the union of the two answer sets is all of n, you're not going to get the maximal elements. You are going to get the decidable subsets, and those would be the decidable oracles. So those would be the oracles that you can actually compute already without anything, and they are terribly boring. Okay? So you don't want those. That's the wrong thing to say. But here you just trust domain theory. You say, oh, the total oracles, they will be the maximal elements. Then you calculate the maximal elements, and they are the thing that they should be. So we have the oracles. How about Turing reductions? So classically, a Turing reduction is a map that takes oracles to oracles, or partial oracles to partial oracles. You feed it an oracle on the tape, and it's a Turing reduction if it's realized by a Turing machine. There has to be an actual Turing machine that performs the reduction. So how do we say that synthetically? Well, it's going to be somehow domain theoretic, because we have we have a nice domain in, O is it's a DCPO, so things are going to get domain theoretic. So let's just recall that if I have omega algebraic DCPOs, so countable base of compacts, directed complete poset, if I have a map like that, it's said to be Scott continuous if it preserves directed suprema. And let's also define its graph. So this is now standard domain theory. So the graph of such a function is the set of pairs DE, which need to D and E are compact, such that E is below f of D. And the way you think about this is the graph already holds all the information that you need to know about f. You can reconstruct your f from this set by a directed supremum. And the E is below f of D, information theoretically says, oh, if I know that D comma E is in the graph, what this tells me that if I feed f an input that information theoretically is at least D, then I will get an output that is at least E. Okay? So what would be a Turing reduction? So so certainly it's not going to be an arbitrary map from O to O. But also, it cannot be just a continuous map from O to O, because constant maps are continuous. But not every constant map is a Turing reduction. If that were the case, I could reduce any oracle to any oracle by constant map. So that doesn't make any sense. And so the correct definition turns out to be this. A Turing reduction is a Scott continuous map, which additionally has a countable graph. That's what we want. Where does this come from? Well, this comes from the idea that the function is realized by a Turing machine. Because it's realized by a Turing machine, there's a classic theorem in computability theory saying that a map is Turing computable if and only if its graph is RE, is countably enumerable. And that's just that, but it's now stated synthetically and for arbitrary domains. So now we have a notion of Turing reductions for at least omega algebraic DCPOs, so also for our domain of interest. So the theorem we would like is sometimes called the Kleene-Post theorem, namely that there exist incomparable oracles. What does that mean? That there exist two oracles such that no reduction will map one to the other. So the classical proof goes a little bit like this. It's called, sometimes called the finite extension method. You start with two empty oracles, and then you keep extending them. So at each step, so you build the two oracles, which I'm now writing now as the oracle x and y. So x is a pair of sets, and y is also a pair of disjoint sets. So you have your two oracles, x and y. You build them like this. You start with empty, empty. And then at each step, you extend them by some finite amount, making sure that as you do that in the nth step, you make sure that the nth Turing machine cannot possibly reduce x to y or vice versa. But to know how to extend at each step, you need to decide a question that has the power of the halting set. So this is a genuinely classical construction, and it results in oracles that are computable in 0 prime, so in the halting oracle. So we cannot do this purely constructively. It's impossible to do this purely and constructively. We really are using here some classical reasoning. But when you stare at this, it starts to look a lot like the bare category theorem. So the bare category theorem is a theorem that says it has many forms, and for the omega algebraic DCPOs, it holds, and it says a countable intersection of sets with dense interiors is dense. Now, usually people say a countable intersection of open dense sets is dense, but for us it'll be more convenient to say it in this equivalent form, which just looks at the interiors of arbitrary sets, and those need to be dense. This proof uses dependent choice, and so it's valid in the effective topos. And no, it doesn't use any classical reasoning. Why am I saying that the above argument is related to the bare category theorem? Well, because this finite extension method, where you are building ever longer segments of the oracles, really corresponds to starting in some open set and then narrowing down to some limit point. And that's how the bare category theorem works. It also works by an iterative method where in the nth step you make sure that you forever stay inside the nth set, and so your limit point will be in the intersection of all of them. So it looks like we have to do something of this kind, and indeed we can, because synthetically there are only countably many Turing reductions. So let's look at how we would like to do this. So let's try to use the bare category theorem. So I'll try to use the bare category theorem to actually prove the Klini-Post theorem. Okay, so the first observation, which is the only synthetic observation here, is that there is an enumeration, rho, of all Turing reductions between partial oracles. And this uses the Enumerability Axiom. Okay, so there are only countably many conditions to worry about. So then you write down the sets, just like in a book on computability theory, when you look at how these things are proved. You say, okay, so what am I doing? So the nth set should be the set of all pairs of oracles x, y, such that the nth reduction maps neither x to y nor y to x. And now I would like to find something that's in the intersection of all of these Rn's. So, are the Rn's, do they have dense interiors for the Scott topology and O? And the answer is not quite, okay? But they are sufficiently like sets with dense interiors. Let's quantify how we do this. So in order to do this, we're now going to have a short interlude on a favorite topic of Jaap's, J operators in the effective topos. So, why? Because I will have to speak about something being computable up to a halting oracle. That's where I'm going. So now I need a synthetic way of saying that. So if you take a closure operator, so that's an operator that has some nice properties. So it's monotone, inflationary, preserves finite suprema. So J, if it's every such operator, it actually induces a modal operator box on all objects. And I'm not going to go into details of this. And during Andy's talk, I worried that the formula is wrong. So please, somebody put me out of my misery. So what is this box A? Well, the box A, the way you think of box A is like this. So think of A as an object where every element has some computational evidence. Now, box A is going to create a slightly larger set where this computational evidence has been relaxed a little bit. Well, how was it relaxed? Using the J operator. Now, the important observation is, and you can find this in Jaap's book, is that if you have any predicate, there is going to be a list J that forces it. So in particular, there is a list J which forces the principle of the limited principle of omniscience. So there is a list operator J such that for every function from natural numbers to 0, 1, it is J the case that the function either attains a 1 or it doesn't. Without the J, this is known as LPO. It is the logical way to express the fact that the halting set is decidable, or the internal way of saying the halting set is decidable. So what I want is I want the least modal operator that forces the fact that the halting set is decidable. And I will just use this one, but in principle I could use also any larger J and all the proofs would still go through. I would just get weaker results then. So now I can tell you what the intuition behind this is. This is some fairly complicated stuff about model operators that I think Andy doesn't like. Did you say you didn't like model operators? Model logic as a whole, I see, yeah. Okay, so what I find interesting, what I find very interesting here is that, you know, rather than what, you know what logicians do? Yeah, well, logicians really like to study model operators and model logics, and they come up with all kinds of logics, but they never use them. But here, we have an actual mathematical use of model operators. Which I find refreshing, that you actually get to use them for something. So how do you think of them? So you can think in the effective topos, in general, you can think as elements of A, arrow B as maps, computable maps. So they're computable with respect to whatever underlying realizability representation the A and the B have. But nevertheless, they're the computable maps. Whereas if you look at the maps from A to box B, for this particular box from the previous paragraph, then they will be computable relative to the Heyting oracle. And this brings in a way to speak about non-computable things in a topos where everything is computable. And by the way, this propaganda that everything in the effective topos is computable, it's clearly false, because the effective topos actually contains classical sets as a subcategory. So yeah, it's computable, but you know, in a trivial way, at least on the sets. So you have to be a little bit, you have to understand what that means a little more carefully, like in what sense are things computable in the effective topos. And there is a way to speak about computable relative to the Heyting oracle using model operators. So we can now go back to the clean post. So of course, we're not going to do this just for one particular domain, because it's very easy to just do it for any domain. So we're going to work with some arbitrary domain D, so more specifically, omega algebraic DCPO. And suppose we have R. So let's go back to the usual notion of density first. Okay. So suppose you have R, and this R has dense interior. Now, if it has a dense interior, that's a kind of a for all exists statement. And using countable choice, in this particular case, you will be able to obtain a witness for density. And this witness is going to look like this. It's going to map compact elements to compact elements, H. Okay, so this is now a computation. That's a witness for density for the density of the interior of R. For each compact element D, H of D is going to give you some bigger compact element such that the basic open set determined by that compact is contained in R. Once you have this H, you know that the interior of R is dense because you take your element X, there's some compact below it, you find this H of D, it's immediate. Okay? So this is another way to say that you have a set with a dense interior, that you have a map like that. So once you have, so now suppose, let's prove the clean post. So once I have such witnesses, H0, H1, H2, for some sets R0, R1, R2, how do I inhabit their intersection? I inhabit their intersection by starting with some arbitrary D0, so that's going to give me density, start with some arbitrary compact set, and then the supremum of the chain Dn will be in the intersection. What's Dn? Well, what do you do? Dn plus 1 is just H of n of Dn. So H of n is making sure that we stay inside Rn. And this is how the proofs work. Like if you look at the proofs of bare category theorem, or they're going to look like that. So the question is, in our case, do we have such an H? And the answer is, for our sets Rn, the ones that we had, the ones that were defined using reductions, the answer is, well, no, we don't get the H. What we get is H with a box stuck in it. So we can calculate these compact elements witnessing density relative to the Heyting oracle. So it's a model map now. But we can get out of this because every omega algebraic DCPO is an algebra for the box. You can go from the box D back to D. So we can do some monady thingy and have a slightly more complicated construction, which people who think about computational effects and functional programming will like. That gives us the following theorem. So say that a subset R of D has box-dense interior, not if we have this H witnessing the density, but H has the box. So it maps from KD to box KD. So it's a little too weak to give us the actual density. Okay? So that's box-dense interior. Okay, so here's a statement. In an omega algebraic DCPO, a countable intersection of sets with box-dense interiors is dense. That's the synthetic Kleene-Post. What happened here? I replaced omega CPOs. So the original theorem, the original Baire category theorem, only required suprema of chains. But now, because I have this box, I require suprema of directed sets, so a complete enough object, and then I can recover my Baire category theorem. This theorem is pure. Examples are easy to find. So how do you get the usual synthetic post-Kleene theorem out of it? So the classical one, there exist incomparable oracles in the synthetic computability. Well, we just apply this theorem. So we need an omega algebraic DCPO, and we need some sets which are with box-dense interiors, and then their intersection. Okay, so well, they are exact. It's literally the thing we started with. So our omega algebraic DCPO is pairs of oracles, so O cross O. The modal operator is the halting modality. And the sets are the ones that we wrote down, namely the ones that will guarantee that so Rn guarantees that the nth reduction does not reduce x to y or vice versa, and it's actually not that hard to verify that these do have box-dense interiors. So we get our Kleene-Post, synthetic Kleene-Post this way. Well, this is the particular one. I consider this to be synthetic one, this proposition, which is about arbitrary DCPOs. And so we have a modal Baire category theorem. So that's the Kleene-Post theorem from computability theory. So I'd like to finish up by telling you that we are not stopping here with Andrew. We're also thinking about the synthetic Friedberg-Muchnik theorem, which is an enhancement of the Kleene-Post, because it doesn't just say that there exist incomparable oracles. It says there exist incomparable computably enumerable oracles, which means that the set A1, so the set where you get the answer yes, that one needs to be computably enumerable. It's a more involved construction that uses a method known as the finite injury priority method. So how do you synthesize that? It's ongoing work, but I can explain what the correct notion seems to be, okay? So when you stare at the finite injury priority method, you come up with the following notion, which I'm not sure how much we will be able to optimize it. So say that a subset R of D, it has fallback dense interior, okay, if a certain thing happens. But before you read that, let me tell you what the intuition is going to be. So somebody asks you to produce a witness, and you have a candidate for this witness unless something goes wrong. But you don't know if that thing is going to go wrong. So what you want to do is you want to say, here's my candidate for the witness. And then if later on somebody comes along and says, no, there is a problem, you have a fallback. You say, oh, what is the problem? No, okay, I can fix this. So you have a candidate, and if it ever turns out to be wrong, you know how to fix the problem. Okay? So now you're supposed to say, well, what's going on? Well, okay, classically, this would be very easy. If I could use excluded middle, I would say, is there a problem? If there isn't a problem, the candidate works. If there's a problem, well, then I will use one of the fallbacks. So classically, I'm not doing anything, but I'm not classical. So I'm doing something, okay? So I am slightly weakening my notion of density in a constructively sensible way, in an interesting way that is completely invisible if you're doing just classical logic. So let's now read the notion of density here, okay? So I'm supposed to show you why R is dense above D. And I can find a candidate C, okay? But there is an injury set, so a set of problems that could injure my C. I'm using the terminology of the finite injury priority method here. So you could also say, instead of injury set, you could say obstruction set or something like that. So such that what happens? Oh, I'm very sorry, the first bullet is wrong. The first bullet should say the open set above C complemented with I, not intersection. It should be complement, okay? Complemented with I is inside R. Okay. Now, if I is empty, I'm done, because then there is no problem if I is empty, okay? However, maybe I is not empty, and I see that I impolitely shadowed one D with another one. So the second bullet says, whenever there is a problem, I can find a fallback that removes the problem, okay? So here's the definition again. And so now, what you get is the following. If you have an omega algebraic omega CPO, so careful now, it's not a DCPO anymore. It's an omega CPO. So it will only have suprema of honest chains. So no monkey business with boxes anymore. It has to be an actual chain. So in an omega algebraic omega CPO, if you have a countable intersection of sets with fallback dense interiors, and now for the Lawson topology, which I find beautiful, so that's another topology that's not Scott topology, but I need the Lawson topology because reductions involve both positive and negative information. So for Lawson topology, this holds. So we think we have this theorem, okay? And that's the synthetic Friedberg-Muchnik. And from it, it's then very easy to get the classical one, and many others. So I'm going to stop here, except for saying what the omega algebraic lattice, where do we apply this one? Well, you have to apply it to the space of CE oracles. What are the CE oracles? Well, there will just be the omega algebraic lattice of countable subsets of N, because countable subsets means CE sets. Here's a quote to end with. Thank you.
Okay, I think we can take a bit of time for a few questions, but lunch is waiting. So, are there any questions? Sorry, the back. By the way, I
think the people who are recording really want you to carry the mic around, because otherwise the questions are not audible.
Thank you for the talk. So as an excuse for this question, you mentioned that it is hard to explain the definition of the effective topos to people. Would you say that the structure of the category of assemblies would be sufficient or insufficient to do syntactic computability? So without being able to take questions all the time.
Okay, so yes, that is a very good thought. So often when I'm faced with explaining what the effective topos is, I instead explain what assemblies are, because it is like 10 times easier to explain. And then I say, and the effective topos is just slightly more complicated, and people just believe that. As far as doing synthetic computability in assemblies goes, you could do a lot, a great deal, so long as you're not using anything essentially impredicative, because the assemblies are a predicative model of type theory and intuitionistic logic. You don't get omega. Omega is not, the sub-object classifier is not an assembly. So these model operators, for instance, you could still define them, but just not in the way that refers to omega. In fact, Andrew has a very nice formulation of the halting oracle modalities in type theory using ideas from homotopy type theory. That's at his last type stock. So you can, I think you can do a lot. Probably you can do everything. I'm not sure. I usually phrase things in terms of the topos because it's, I don't have to worry about the predicativity dimension of things. I just work. But yes, I think most of it can probably be done in assemblies.
Okay.
Yes, so thanks for your talk. So as you pointed out, the Kleene post is just a classical forcing construction where you can use the bare category. So for Friedberg-Muschnick, in order to phrase it as a forcing construction, you have to do something extra, right? So classically, this was done by Jockusch. I don't know if you're aware of that. He introduced this notion of E-genericity. So his way of doing it is looking at the space of all enumerations and do a forcing construction over that. Is what you are doing with the fallback dense interior, does that translate back to doing forcing over that space of enumerations? Or?
I should look at that. Andrew and I were, our starting point were the more basic classical formulations of finite injury priority method. So we just, like, you open source book or one of the books that has, on page 15 has the Friedberg-Muschnick theorem, and then it says, it explains the finite injury very concretely, just on one example. And so that was our starting point. I would expect that whatever we got synthetically is going to correspond to something that somebody did in computability theory a while ago. It is extremely difficult to discover new ideas in mathematics. Up there.
Yeah.
Thanks, interesting talk. Are you aware of the work by Bob Harper and John Sterling on synthetic Tate computability?
Synthetic, say again, Tate. Yes.
So it's parametricity using subtyping.
So that's a different. That's also a kind of synthetic mathematics, which is sort of it's designed very much for things that logicians and programming languages people do, and type theorists. It's a very nice piece of work. Yes, I'm aware of it. Let me say this: the Tate computability has nothing to do with computability. That's maybe good to know. But yeah. Right. So the box is, so the box appears there, yes. Yeah, but they're logicians, you see. This is actual, this is topology, right? Yeah, it's a very nice piece of work. It's really, yeah. Thank you for reminding me. Yes, there are boxes there, yes, thank you, yes.
Okay, well, let's say
I think you have to let Jaap speak, he wanted to speak.
Did you? Sorry.
Thank you very much. I just have a question about your the way you describe the synthetic analytic dichotomy. And so when I think of homotopy type theory, what you do is you define basic concepts. For example, you already defined sets. And then you prove things about them in a big foundational system, which is type theory. So that is just what you listed under the analytic kind of mathematics, right? Yet, you talk about the homotopy type theory as something synthetic.
Right. So I think this touches upon the fact that we're trying to do synthetically not just the study of a single structure such as the Euclidean plane, but an entire branch of mathematics. And like smooth analysis, computability theory, homotopy theory. And it is in the nature of these branches that they already require a very rich environment in which they express themselves, such as type theory, or higher order logic, or set theory. So yes, you're entirely correct. It's going to look like an analytic method. Maybe what distinguishes the synthetic approach is the fact that we do not insist on a single unifying foundation. So we are willing for each branch to have its own special axioms in addition to some common core, which we would call the foundational system. And these axioms are wildly incompatible with each other. You can't put them together. So to my mind, that is maybe a more important characteristic of the synthetic approach than this theory model thing. I agree with you. Maybe the theory model thing I presented more for pedagogical reasons, but I think you have an important point there. So yeah. In a way, as humans, I think we would naturally gravitate towards having a foundational system. Because as a mathematician, you would like to work in an environment that is extremely rich. But that means that you will want a foundational system that is very expressive. And a system that is very expressive, but then it will be foundational because it's so expressive. There's no way out.
But there is a way to lunch. I don't know. It's just outside, I guess. Yeah. Outside. Yeah. Okay. So and we should reconvene at 1 o'clock. No, 2 o'clock. Yeah. And then, yeah.